Hi, so in this video we continue with the previous one. We talk about the slack and critical path for the example we had, which is to remind you of that example. Here's what we had. So this is our uh, example of these activities where we have the durations of all activities and we have the earliest start time, the earliest finish time here, the latest start and the latest finish. Now from this information we want to compute the slack uh, and find the critical path. So some delays affect the overall project completion date, others may not. So we want to complete the slack for each activity. Slack time by definition is the amount of time an activity can be delayed from its earliest start without delaying the project's estimated completion time. If an activity has a zero slack, it's called a critical activity. And critical in the sense that if there's a delay for the activity, the entire project gets delayed. The critical activities are part of the critical path. Okay? So the critical activities form at least one critical path. There may be more than one critical path for the project, which means different ways to lead to earliest completion time. It is helpful to have a graph, the arc on network graph, to list all the paths and determine if there's more than one path exists. So the critical path is the longest path in the network. The sum of the completion times of the activities on the critical path gives the minimal completion time of the project. Okay. So having done that, let's see how we complete the slack. So the slack of each activity is really simply can be computed by taking the latest start minus the earliest start, or the latest finish minus the earliest finish. So in our example, there will be two activities, C and D, with a slack of 1, and all others would have a 0 slack. So if we go back to the project, and so it's going to be this minus this, or this minus this, that's a 0. This minus this is 0, so this is a critical. This minus this is 1, so that's not a critical activity. This minus this is 1, or this minus this, that's the slack of 1 here. And this is a slack of 0 because this minus this is 0. So this is on the critical path, and this is critical by definition. So my critical path would be this. So these are my critical activities which constitute the critical path. And if I add the durations here, 1 plus 3, 4 plus 9, 13 plus 1, 14, which is the earliest completion time for my project. Okay. So if I look at this path, that's not the longest. It takes 1 plus 7, 8, and 4, 12, 13. So that's not the longest path. And also we want to compute the free slack. A free slack by definition is the slack is how much an activity can be delayed without delaying any activities that come after it. So this activity has 0 slack because if I delay it, I would delay this and this. This activity would have 0 slack because if I delay this activity beyond its earliest time, this is going to be delayed. If I delay this activity, this will be delayed. However, if you look at this one here, if I delay this activity beyond the earliest time by 1 day to 13, this would not be delayed because the earliest start is 13. So I have a free slack of 1 for this activity. Okay. So that's where we can talk about the free slack is the maximum estimated time that an activity I may be delayed beyond its earliest start without delaying the earliest estimated start time of any subsequent activity. So that's the mathematically, you can take for activity I, you pick all activities that are immediate successors. For each one, you compute ESK minus EFI for activity I, and you pick the minimum value for those, and that gives you the free slack. Okay. We talked about the critical path, the longest path in the network. The Gantt chart, let's do a Gantt chart for our example. And in this example, we have for activity A, we have the earliest start, earliest finish, latest start, latest finish. So all critical activities will have their earliest start and latest start are the same. So there is no slack. For this activity C, you can see that that's the earliest start, earliest finish, latest start, latest finish. And displaying these activities like this will help you with the management of the network. So if you are in this, so as the dates go on, suppose you are here and you're looking at what have done, so you know that 2 activities have been completed. You are in the middle of this activity and this activity, and there will be 2 more activities to complete. Also, you can tell the slack for each activity, which ones are critical, which ones are not, by just simple graphical display. Okay. Now we want to introduce random variation into estimating activity durations. So in reality, activity times are probabilistic in nature. We'll treat them as random variables, and which means they are sources of randomness. And as random variables, they should have a distribution associated with them. The problem with the distribution here is that we cannot have data because each project is different, and so once we decide on the activities, usually the way we find the distribution is we look at historical data, we do a histogram, and we find out the shape of the histogram, and that tells us what our distribution is. Well, in this case, there's no data. So how do we pick a distribution? So because there is no data, so now we ask ourselves questions like, what's the minimal duration that activity can take? What's the maximum it can take? What's the most likely it can take? And from this basic information, we can identify a distribution which is called the beta distribution. And this is good. This is a distribution that's good to select when there is no data to formulate an actual probability distribution. So it gives you a pretty good idea from these 3 estimates. So the method is called the 3-parameter approach. Okay. What's that? So the mean. So now we are given the most optimistic duration activity, we call it AI, the most likely, call it MI or the mode, and the least likely or the pessimistic approach, we call it BI. And from these 3 numbers for each activity, and knowing that the distribution is beta, we compute the mean for each activity and the variance for each activity. Okay, and these are approximations, of course. So that means if I take Ti, which is the duration of activity I, we think of it as a random variable, and the behavior of Ti is approximated by a beta distribution, which is characterized by these 3 parameters, AI, MI, and BI. So the pessimistic, the mode, and the optimistic estimates. Okay, and now from these 3 quantities, we estimate the duration of each activity, the expected value of Ti, which is given by this formula, AI plus 4MI plus BI over 6. And the variance for each activity is BI minus AI over 6, and you square that. Okay? So we make some certain assumptions that in order to proceed with this, the critical path can be determined using the mean completion times for activities as if they were fixed completion times. So this would give us the expected time to complete the project is determined solely by the completion times of the activities on the critical path. We're just taking the means. The time to complete one activity is independent of the time to complete any other activity. So these assumptions really allow us to proceed. We need one more, that there are enough activities on the critical path so that the distribution of the project completion time can be approximated by a normal distribution. That's by using the central limit theorem. You may recall that the central limit theorem, if you take a large number of random variables, you average them, you end up with a standard normal distribution. If you don't average them and you add them, you end up with a normal distribution, not necessarily the standard one. So let's apply this to our example, and let's assume that the activities we had are the mode, the MIs, the most likely duration times, and let's assume the pessimistic estimates are 20% smaller. So the optimistic are 20% smaller and the pessimistic are 20% larger than the duration times. So that, let's say, MIs are the ones we have, AIs are 0.8 MIs and BIs 1.2 MIs. So if I would tabulate these, this is what I would end up. So these are my activities. These are my precedence relationships. These are my most likely ones, the one I had before, 1, 3, 7, 4, 9, 8. And I picked the AIs, the optimum value. These are usually given as 80% of those values. They don't have to, I could change them, but that's a good choice for this example. And the pessimistic estimates the BIs as 20% more, so they are 1.2 times those values. So I got those values here. Okay, so this is usually the given data for this problem. Now from this data I want to compute the mean mu I for each activity and the variance sigma I square for each activity, okay, using those formulas here. Where are they? Using the, so AI plus 4MI plus BI over 6 gives me the mean, and BI minus AI over 6 squared gives me the variance. So if I pick this activity, this one would be this plus 4 this plus this over 6 gives me that, and the same thing for all of them. So please, you need to complete all of these before you proceed. And for the variance, I take this minus this over 6 and square that, so I get the variances here. Okay, so remember, I need the variances, not the standard deviations. Don't take square roots. We need the variances, full variances. Okay, now the next step, I want to let t be a random variable that represents the total time of the activities along this path. This is the path, ijk is the path. So this is my random variable is ti, tj, tk, etc. And mu would be the expected value or the mean of the t. So with our, and this is true whether the activities are independent or not, as we illustrate in the attachment if you want to see it. For my critical path is consists of activities A, B, E, F. So I want the mean of that, which is the expected value of the random variable, which is the duration of the critical path. So I take that's going to be equal to, this is the steps, that's the mean of this, which separates them. So that's the mean of A plus the mean of B plus the mean of E plus the mean of F. So I add the means of the activities on the critical path, which gives me 14. Second thing, I want to compute the variance on the critical path, and then basically I add the variances of my individual activities as I calculate them in the table. So the variance for my path A, B, E, F would be the variance of A, variance of B, variance of E, variance of F. I add them up, and that's going to give me a value of 0.4088, and then I find the standard deviation by taking the square root of this value, which is 0.63. It's very, very important here to remember, don't find the standard deviation of add them. That would give you the wrong answer. So if you are asked to find the standard deviation of the critical path, find the variances of the individual activities, add them up, you got this answer, and then take the square root to find the standard deviation. Okay, now by the central limit theorem, my path, which is this, the t on the critical path, is supposed to be normally distributed. So that means, because it's bell-shaped, I can compute the probability of t being less or equal to x. And the way I do that is I find the z-score for x, which means taking x, subtract its mean, divide by a standard deviation, where I know now the mean and the standard deviation, because my mean is 14 and my standard deviation is 0.6394. Okay, so I can find all sorts of probabilities. So if I want to find out what's the probability of t duration of the critical path that will be completed in 14 days, would be P of z, and I find the value of the z-score of 15, which is 15 minus 14 over the standard deviation. So that's the probability of z less than 1.56. I go to the normal table to find that value being 0.94. So you have to remember how to use the standard normal table, the z table, to compute these probabilities. So if I want to find out what's the probability of this path, say, exceeds this path, then I remove the common activities. That would become the probability of TC greater than TB, or the difference being greater than 0. So in this case, I need the z-score of 0, and I need the duration for CD is 7 plus 4 and BE is 3 plus 9, and I want to divide by the standard deviation of these activities. So I want the variance of this activity, variance of C, variance of D, variance of B, variance of E, add them up together, take the square root, and then that would give me a normal distribution with a z-score of 1.20, and since it's larger than, I want this area up in the normal curve. Okay, so that's P of TC minus TB greater than 0 would be z, that's the z-score 0 minus -1 over 0.83, and then we look up the probability in the z table. Related questions. So now I can ask all sorts of questions. What is the probability that the project will be completed within 13 days? Can you find that? What is the 95% confidence interval estimate for the number of days to complete the project? So with 95% confidence, how many days I have to complete the project? What is the probability the project will be completed within 14.5 days? What is the probability the project will take longer than 13 days? What is the upper limit on the number of days within which we can be virtually sure, 99% sure, that the project will be completed? We know that the 14 days, we are 50% sure we can complete that. So how we can, please try to answer all these questions, and they are all reduced to basically working with a z distribution. Okay, and the Next project and the next video we'll talk about cost considerations.